Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to today's lecture on advanced transition metal organometallic chemistry. We have been discussing half sandwich complexes of cyclopentadienyl ligand in the last few lectures, and in the last lecture we have exclusively looked into transition metal cyclopentadienyl nitrosyl complexes. We have looked into the structure, reactivity and the preparation of these complexes, and today we are going to finish a little bit of discussion which is left on transition metal cyclopentadienyl nitrosyl complexes before I take up today's topic, which is on transition metal cyclopentadienyl hydride complexes. Now, if I recapitulate in our past discussion, this transition metal cyclopentadienyl nitrosyl complexes can exhibit two kinds of binding. One can be linear, another can be bent. This type of binding can be easily characterized using X-ray as well as infrared spectroscopy. Now, we have looked into several examples in our last lecture where these metal nitrosyl binding have been characterized using X-ray that looked into the metal nitrosyl bond distances as well as metal nitrosyl bond angles depending on the binding, and correspondingly that was also verified or supported by infrared spectroscopic data. Now, we have also seen that the nitrosyls, when they bind as a 3-octet donor, they bind in a linear fashion, which results in a very shorter or metal nitrogen bond, and that means that it is a stronger metal nitrogen bond, and hence at the infrared new stretching frequency appear at higher wave numbers. And when the nitrosyl is bound in a bent fashion, it uses a single electron, hence it is a weaker binding, and hence the metal nitrogen bond now is longer, and as a result the frequency of the new NO is also appear at a lower frequency. Now, having said that, the next we are going to discuss about a particular interesting example in which people make a chiral compound of half sandwich transition metal cyclopentadienyl nitrosyl complexes, and then they study their configuration, retentions or various reactivity under optically active environment. So, we are going to talk about chiral cyclopentadienyl transition metal nitrosyl complexes. So, one can sort of envision that this transition metal is bound to Cp and 3 other ligands, the second ligand being nitrosyl, and the third and the fourth has to be 2 different ligands. One can be carbon monoxide and the other can be phosphine. So, let us take a look at the preparations of these interesting compounds. And preparation procedure starts with a sequence of reactions. The first obviously of that sequence is simple preparation for transition metal nitrosyl complexes starting from transition metal carbonyl complexes. So, the reaction is as follows: C5 H5 Mn CO3 reacting with NO plus P F6 minus, eliminating a CO to give C5 H5 Mn CO 2 NO plus. Now, one thing that one needs to see over here is that one of the CO is getting replaced by NO, and we had discussed about replacing the COs by NOs, and in our earlier discussion we had said that if a single CO is replaced by a NO, then a positive charge is introduced, and that is exactly what this reaction turns out to be. Another important thing of this particular reaction is that even though we have this notion of carbonyl being very tightly bound to the transition metal because of ligand to metal forward donation and metal to ligand pivot backward donation, but it turns out that the NO can replace a tightly bound CO and make a metal nitrosyl complexes. Now still C5H5Mn dicarbonyl nitrosyl is still not a optically active compound. So, one then needs to further replace one of the COs with another ligand, and the reaction is done with phosphine with the elimination of another CO. So, in this case the phosphine replaces CO to give this C5 H5 Mn CO NO PH3 plus compound. Now, this is a optically active compound in a cationic form. Now, one also sees an important trend which is emerging over here, that in both of the reactions the carbon monoxides get replaced first by NO, and when this dicarbonyl nitrosyl is treated with phosphine, the nitrosyl does not get replaced, but instead another carbonyl get replaced to give carbonyl nitrosyl phosphine compound. So, this is the interesting observation is that these CO gets replaced by NO first and then by phosphine second to give this optically active cation. That then reacts with any chiral nucleophile like R O star minus produces the corresponding acid. Okay. So, this sort of is the optically active compound, which is somewhere like Mn star and this right now is a diastereomer because of two chiral centers. This is a diastereomer because of two chiral center and can be separated using the particular enhanced solubility of one particular diastereomer over the other, resulting in isolation of chiral compound. So, this is a very interesting technique whereby a chiral cyclopentadienyl transition metal nitrosyl complex has been synthesized, and then the subsequent isolation of a particular in its optically active form is achieved by making the ester with a chiral ancillary and then exploiting the fact that one of the diastereomer is more soluble over the other, and like taking advantage of the differential solubility, one can then separate this optically active compound. Now, what this reaction underlines though is that the stronger binding of NO NO binding is stronger as observed from the preferred substitution of CO. So, what is important over here is that the phosphine knocks off another carbonyl and not a nitrosyl, thereby indicating that NO binds strongly to the metal center. So, with this we will sort of close our discussion on transition metal nitrosyl complexes and then move on to transition metal cyclopentadienyl hydride complexes. So, these are important complexes cyclopentadienyl transition metal hydride complexes. These mainly are observed for 4D and 5D metals. And for 3D these are usually not observed because 3D hydrides are extremely reactive and 3D metals dimerizes with the loss of hydrogen gas. However, the 3D metals dimerizes with the loss of hydrogen gas. So, some of the examples of these complexes are as Cp2 zirconium dihydride, which sometimes can be in aggregated form, or Cp2 niobium trihydride, Cp2 tantalum trihydride, Cp2 molybdenum dihydride, Cp2 tungsten dihydride, Cp2 technetium hydride, or Cp2 rhenium hydride. Now, these transition metal cyclopentadienyl hydride complexes, so many variants of these are known, and one of their importance arises from the fact that they are important catalytic intermediates in many organometallic catalytic transformations, and hence arises interest and have also been extensively studied. So, we are going to look at some of the preparative methods available for preparing these transition metal hydride complexes, and the simplest of all involve the reaction of metal halides with some kind of hydride source, which are usually borohydrides, and also a cyclopentadienyl source, resulting in the formation of this transition metal cyclopentadienyl hydride compounds. So, for example, the reaction of MoCl5 plus 2 NaC5 H5 plus NaBH4 in THF minus 78 degrees centigrade. The reaction is the low temperature and then warm up to 65 degrees centigrade, giving C5 H5 whole 2 MO H2. Similarly, the reaction of ReCl5 plus NaC5 H5 giving C5 H5 whole 2 ReH. Now, this yield is kind of an issue 30 to 40%, and the moiety has been characterized in proton NMR, where the rhenium hydride appears at minus 23.5 ppm. So, this metal hydride appearing at highly upfilled region, which is at minus 23.5 ppm, whereas this 5 proton of the C5H5 appearing at 3.64 ppm. So, the proton NMR is kind of extremely informative, and it is very simple because it has 2 peaks, the peak at 3.64, which belongs to this C5H5 appearing as 10 integration ratio 10H, whereas the hydride appearing as 1H. And another important thing is that BCP rhenium hydride, however, is a air stable compound and diamagnetic, air stable and diamagnetic. Diamagnetic. As a result, these can be very extensively used in applications of organometallic chemistry in proton NMR spectroscopy. So, the diamagnetic, it arises from a 18 valence electron rule. So, 2 Cp is 5 into 2, 5 electron into 2 plus manganese technetium rhenium is in the same group 7 plus 1 equals 18 valence electron diamagnetic compound. And because of this additional stability, this compound was largely used for first proton NMR applications of an organometallic compound. So, this was studied from that perspective. The structural characterization of this compound showed that the CP rings are tilted and they are not parallel to each other, unlike what was observed in case of the metallocene chemistry. So, let me illustrate that with this diagram. So, Cp rhenium hydride has a tilted Cp ring similar to that of the molybdenum complex. similar to these have tilted SCP rings. Now, another interesting thing about rhenium complexes is the fact that at higher oxidation state they can accommodate large number of hydrides. For example, rhenium 7 complexes can accommodate a large number of hydrides. For example, this Cp star rhenium chloride in presence of lithium aluminum hydride LiAlH4 and methanol produces this rhenium hexahydride peak and the stretching frequency of this rhenium hydride is 2018 centimeter inverse. Now, these are fluxional molecules, so you can see the dynamic exchange between the axial and the equatorial hydrogens. As a result, at a very low temperature 90 degrees centigrade, proton NMR shows axial and equatorial hydrides, whereas at a much elevated temperature 60 degrees centigrade coalescence of signal occurs due to rapid exchange. Now, this shows that these hydride exchanges are sort of becomes very rapid at higher temperature, and as a result single coalescence happen at higher temperature. Another interesting property of these transition metal rhenium hydrides are their reactivity, and these hydrides are generally prone to protonations. Cyclopentadienyl metal hydrides are prone to protonation. For example, these I am illustrating using this C5H5 whole 2 MH2 in presence of H plus, giving C5H5 whole 2 MH3 plus. M can be molybdenum tungsten. Similarly, C5 H5 whole 2 rhenium hydride can protonate to give C5 H5 whole 2 Re H2 plus. Now, once protonated, they can also be deprotonated by using a base like OH minus, and the same applies over here. So, what is interesting to see that these hydrides are very hydridic in nature. When bound to electron rich 4D and 5D metals. So, the electron rich metals make them very hydridic. As a result, they get protonated easily, and these can be observed over here. And once protonated, they form cations which can be deprotonated using nucleophile such as hydroxide ion. Now, with this I would like to conclude my today's lecture on transition metal cyclopentadienyl hydride complexes. Today in particular, we have looked into two things. We finished up with our little bit of discussion left on the chiral transition metal cyclopentadienyl nitrosyl complexes, the formation of the chiral complexes, and then took up these topic of transition metal cyclopentadienyl hydride complexes. In particular, we looked into the various preparative methods which are available for synthesizing these complexes, and the method sort of involved direct reaction of metal halides with hydride salts and the cyclopentadienyl salts to form these complexes. Also, we had seen that these metal hydride moieties can be characterized easily by proton NMR spectroscopy, where they appear very upfilled at minus 20 or 30, 25 ppm, and we have also looked into the formation of polyhydrides for higher oxidation states of rhenium, and lastly we have also looked into the hydridic nature of these metal hydrides when bound to 4D or 5D metals, and that can be ascertained by simple protonation reactions which protonates these metal hydride complexes. Now, with this I would conclude today's lecture. I thank you again for listening to this lecture, and we are going to be talking more about transition metal cyclopentadienyl hydride complexes in the next lecture. Till then, goodbye.